is it a pre-recorded session that we'll be having?
I'm going to present.
Okay. So can we have the presentation from you then? Would you tell us something about your research?
Okay, yeah. So I am a research fellow at UCL in London. So I'm working on program repair with Federica Saro and Mark Harman. I'm focusing on repairing APIs. So today the presentation is going to be about the work that we recently published in TSC, where we evaluate the tools. So can I share my presentation right now because it is 10 o'clock?
Yes,
Can I
yes,
share the
please.
screen? Okay.
Yeah.
Okay. Can you see my screen? Okay, great. So please let me know when I have 2 minutes left. So yeah.
Sure.
So as we all know, we have many automatic program repairs tools available in the literature, but we don't know whether these tools can repair API misuses. And this is what we try to answer here in this work. Well, what is an API misuse? When we have an API misuse, actually we violate the specification of the API in the client application. In other words, the clients do not use an API correctly, and then we can have an error at runtime. In the literature, we have found a very comprehensive, let's say, taxonomy of API misuses. You can see a table with some examples here. This comes from MU Bench. And in the paper, we have more details regarding these categories that we have also considered in our paper. So you can see we have cases like missing call checks, missing null checks, missing method calls, missing exception handling, and so on. So we consider this type of bugs here as API misuses. Now, to evaluate the tools, we have 3 research questions. First, we want to evaluate the effectiveness of the tools. Then we want to as a sub-question in RQ1, we want to check what are the reasons of non-patch generation. Then we evaluate how efficiently the tools can generate patches, and then we evaluate how the tools perform to repair different categories of API misuses. For the evaluation of the tools, we check the literature to find all the available repair tools. We concluded on 14 tools that we have used in our study. We have two categories of tools, those that they are the older ones and those that they are the newest one. The 3 last, Avatar, T-Bar, and SimFix, are the new tools, and the remaining are the older tools that we have found in the literature. We want tools that they are publicly available, executable, and configurable. In the paper, again, you can find more details about our selection criteria and why we have excluded some tools from our study. Then for the evaluation, we need to have API misuses at our disposal to evaluate the tools. So because we don't have
2 minutes.
Okay, thank you. So because we don't have such a benchmark, we created one which is publicly available. It is called Api Bench, and you can find this in our repository. For our experiments, we created a framework called API, which is again online and available, and it is easy in use. So let's try now to answer our research questions. So regarding the effectiveness of the tools, most of the tools can repair 30% of the API misuse. Most of them of the patches are plausible, and few are semantically correct. Avatar and T-bar generate most plausible and correct patches. We found that there is an overlapping in the generation of the patches among tools that they are under the same framework, like in ARJA. And regarding the causes of non-patch generation, we found that mostly the tools have incorrect fault localization, technical issues, or timeout issues, and these are the reasons that they cannot repair the bugs. Furthermore, we investigated how efficiently the tools can repair the bugs. Most of the tools need around 4 minutes to generate patches. I must say that we found out that the 3 most recent tools, Avatar, SimFix, and T-bar, can generate many plausible and correct patches, but they are quite slow, these tools. And finally, we investigated the repairability of the repair tools per API misuse category. So we found...
Conclusion quickly.
Yeah. So this is the last slide. So actually, we found that the tools can generate patches for the missing null check, missing value, missing exception handling, and missing call bugs. And the tools take more time to repair missing call, missing null check, and missing context categories. Thank you very much for your attention. You can find more details in our website using our QR code on the right corner. Thank you.
Thank you, Maria. So now let's talk on improving fault localization and program repair with deep semantic features and transport knowledge. So this one is from the researchers from Beihang University from Beijing, China. So can we have the presentation, please?
Okay, thank you, Ritu.
Thank you.
Could you see my slide change?
Yes.
Okay, thank you.
Put that to slideshow.
Yeah. Hello, everyone. I'm Xiangxin. Today, I'm going to introduce our new work, improving fault localization and program repair with deep semantic features and transfer knowledge. And this is the
Please,
outline.
could you go to the view?
Yeah.
Could you maximize the? Could you go to the slideshow? Could you start the slideshow?
Full screen.
Presentation view. Could you go for the presentation? Like I'm able
sorry.
to. Can you go to the presentation view? Let it be. You can go on.
Is it okay? Yeah. Okay, thank you. Yeah. Fault localization method is supposed to generate a suspicious file by analyzing different types of features. And program repair method tries to generate code patches according to the element order from statement level suspicious file. However, there are existing some limitations for FL methods. They haven't fully exploited deep semantic features, and most of them focus on method level. For template-based PR methods, they haven't considered selection orders of repair templates. Thus, we propose the following key ideas to improve FL and PR. Next, I will describe our approach. Let's take a look at the overall framework of our method transfer. In the first phase, we extract methods before and after fakes from open source projects and use a syntax checker to generate 2 large-scale datasets called dataset FL and dataset PR. For FL task, we feed dataset FL to 11 binary classifiers to learn deep semantic features. And for PR task, we feed dataset PR to a multi-classifier to learn the probabilities of different types of bugs. The second phase is FL task. For each the spatial statement in the target project, the already trained binary classifiers are used to generate deep semantic features, which are then fused with two types of dynamic features by an MRP-based model to generate a new suspicious file. The third phase is PR task. We use historical data to fine-tune the multi-classifier, which is then used to predict the probability of selecting each repair template. We construct two large-scale datasets for tasks, but we won't talk about the construction process here due to the time limit. If interested, you can read our paper or watch the 20-minute video. In fault localization task, we first use 11 binary classifiers to extract deep semantic features for 11 types of bugs. The binary classifiers are based on binary bidirectional LSTM. Through such training, each classifier has the ability to identify whether an input sample contains a specific type of bug.
So you have 2 minutes left.
Okay, thank you. Then we use an MRP-based model to fuse deep semantic features with other two types of dynamic features. The model output is then used to reorder the suspicious statement. And in PR task, we train a multi-classifier to predict which repair templates should be selected earlier. The model structure is similar with the binary classifier, except for the output layer. The classifier is first trained on dataset PR and fine-tuned on target project. Finally, it is used to predict a 11-dimensional deep semantic feature for each suspicious statement. In this way, the selection order of repair templates is able to be optimized. Next, let's take a look at the experimental performance. The widely used benchmark defectable J is also used in our experiments. The evaluation metrics and the detailed setups in our experiments can be seen in the table.
Please
First,
conclude. You have 1 minute left.
yeah, okay. First, we compare transfer FL with 6 FL methods. As a result, transfer FL performs best on all evaluation metrics. Then, we compare transfer PR with 4 repair methods, and transfer PR can fix 5 more bugs than baselines. Next, when transfer FL and transfer PR are used together, there are 47 bugs can be fixed, 6 more than the repair method T-bar. Finally, let me summarize our work. We built 2 bug datasets, propose the method transfer, and conduct extensive experiments to confirm its effectiveness. In the future, we will work on extracting deep semantic features of more bug types and exploring deep learning-based patch generation. That's all. Thank you.
So thank you. That was a great presentation. We'll now have the talk on NPEX, which is repairing Java null pointer exceptions without tests. So this work has been done by researchers from Korea University from South Korea. So do we have the authors with us? Yeah. So yes, you can please start with the presentation. So your mic is mute. Can you please unmute your mic and start again?
Sorry.
Yeah.
Sorry. So I'm Junhee. I'm PhD student in Korea University. Today I present MPEX, a technique to fix null pointer generator without test suite in Java program. This work is co-authored with Songchun and Akcho. As you know, null pointer generator is one of the most common errors in Java program. In this work, we focus on fixing null pointer generator as soon as they are detected. For example, we would like to repair null pointer generator reported from users or bug finding tools such as static analyzer and test generation tools. In this scenario, however, existing techniques are ineffective since they require test case, which specify not only crashing input, but also desired behavior. When the bug is reported, however, such test cases are usually unavailable since error reports only describe how the errors are triggered and not desired behaviors. So we present MPEX, a fully automated technique to fix null pointer error without test case. To do so, MPEX automatically imports repair specification to validate patch candidate. Now we explain how MPEX works with the simple MP example. The function is empty, takes a string, and returns whether the input string is empty or not. In this code, MP occurs when the input string S is null. To fix this error, we can easily think of two patches, either returning true or returning false when the input S string is null. Let me ask you a question. Which one will be the correct one? I bet you choose true. If so, you successfully import the correct specification. So how we could come up with this specification? Let's think of what the function is doing with the error input. This function checks whether the length of null string is 0 or not. Then what is the length of null string? Actually, this is an invalid expression which is through null pointer, but it is also natural to interpret the length of null string as 0, like when we consider length of an empty string. Then it's done. We obtain the correct specification, which specifies that the function should return true for null string. Here, the existence of alternative value for MP trigger expression, saying the length of null string is 0, takes a key role to import the correct specification. So far, we have present how to import the right specification for a single example, but it could be generalized to other MP errors. To do so, we run a model that predicts alternative value for NP trigger expression. Then the next step is to symbolically execute a buggy program with the learned model to obtain specification. The key feature of this symbol execution is to interpret NP trigger expression as the alternative value returned by model. Then using the specification, we validate patch candidate, which are generated by using conventional fault localization and patch template. Now we evaluate our technique. In the evaluation, we collect 119 MP errors. 60 are from previous literature, and the others are collected from GitHub. We compare MPEX with two techniques, Genesis and Prefix. Since these techniques require test case, we provide test case for them. On the other hand, we did not provide any test case for MPEX. The results show that MPEX fixes a largest number of MP errors even without test case. Also, to precisely evaluate effectiveness of our technique, we designed our baseline, which use the same fault localization and the same patch template, but use test case as patch validator and not the import specification. The results show that our specification inference technique is effective. This is end of my talk. Thank you for listening.
Amazing research talk. Now we have the next talk on neural program repair using execution-based backpropagation. This one is from Keith Royal Institute of Technology, and various other as well. So now hear them. Yes, you can please start presenting.
Okay, thank you. Hello, everyone. This is Ye. I'm a PhD student from KTH and supervised with Martin. This is the drummer with Matthias. I'm happy to present our work about the neural program repair with execution-based backpropagation. And in the literature review of the program repair, it typically has the three categories of program repair, and our work focus on the learning-based program repair. On the five above mentioned state-of-the-art learning-based program repair approaches, they have two in common. First, they use the neural machine learning translation, typically to translate the buggy code to the correct code and treat it as the natural language processing. And also they use the same loss function, which is the cross-entropy loss, also known as the log loss. So a little bit background of the cross-entropy logs. So this is the summary of the softmax logs inside. And this is the pairwise on the token level. So it maps each token to the token and then is summarized. So if the distribution, it measures the distributions of the expected output and the ground truth. For example, in this example, the lower the value means that it's more close to the ground truth and which means the better. However, there's some problem of the statement of the learning-based token repair because in the learning-based token repair, there's a discrepancy between the core training objective. We want to generate a compilable and correct patches, and the loss function that is purely based on the pairwise token level calculation, which is not something we want to optimize for the network. So here we give the example here. The motivating example shows that the semantic equivalent patch actually receive a bigger loss than the non-compilable patch does because based on the pure pairwise token level cross-entropy loss. And the reason is that because code is not string, code can be compilable and can be executable. So in this work, we want to know to what extent we can embed the unique features of the code, compilable and executable in the loss function. So we propose a reward repair. It contains of the two phases of training, syntactic training and semantic training. These two trainings are actually worked as chain, they are trained alternately. And then first we want a sufficient training of the syntactic training, so they have a really good start points. And then the semantic training act like in the exam or the feedback to give the to update the value based on the execution results. So to provide the feedback or quantify the feedback with three discriminator, we have the difference discriminator, because we note that by only copying the buggy code as the expected output, it could have achieved very low loss value because in the program repair, we only sometimes only need one or few tokens difference, but the other tokens are actually the same. So that means they can also achieve very no cost entry loss, and that's not something we want. So we want to penalty that, and we also want to execute all the predict patches with the compiler to determine the compilability, and then to execute with the human written test suite and the independent automatically generated test suite to determine respective the possibility and the overfitting. So to define the loss, okay, so to divide loss, we want to modulate the regional cost entropy loss because we want to still follow the differentiable, and but we encourage the high quality patches, which is compilable, possible, and correct patches with the 20% of the decrease the loss value, and then the penalty to more than increase the 20% value. So we have set up the experiment to evaluate the effectiveness and the compatibility and the ablation study. So we give a very quick demo. And so demo, this is to fix the 120 physical J bugs for version 1. And then we give the buggy code as the input and also the surrounding context code. And we will generate the patch and then also report the ranking position. And the most interesting, we have put a code and modeled on the Snowdot and the GitHub. And the most interesting things I really think is that we indeed to observe that the ranking positions has changed after we apply the semantic training. So we can see the same bugs and then the different ranking position for that. And so this is the for the impact of semantic training. The more patches are ranked in the top 10, and the average the correct patches has been ranked before. And that's the contribution of the work. And thank you very much.
So thank you for the talk. We'll be hearing from the next speaker, which is on the talk trust enhancement issues in program repair. This work has been done by researchers from National University of Singapore, and we're going to hear the talk from them now. So yes, you can please share your slides and start the presentation.
All right, can you hear me and can you see my screen?
Yes.
Okay, perfect. All right, thank you very much. Thank you for joining this repair session. Also, thank you for joining our presentation on trust enhancement issues in program repair. My name is Yannick Noller, and this is a joint work together with Ridwan Sharifdin, Gao Xiang, and Api Misuse. We are interested in the question about what it needs so that software developers in practice will accept and trust auto-generated patches. So we are asked questions about how do developers want to use APR, what kind of inputs can they provide, and how will these inputs impact the trust of the auto-generated patches. So we started this work with designing a developer survey and distributed via two channels, MSN Turk and also email. Just to give you a brief overview, we had around 35 questions, all with different types. And we had topics like the usage of APR, the availability of inputs, the impact on trust, as I mentioned, but also the usage of APR side products. We received answers from 103 software practitioners. Most of them had quite some experience in software development. And also most of them were actual software developers. We also had software architects and QA engineers, research engineers, and tech leads. The main takeaway from our developer survey was that the developers expect high quality patches in a short time period. So on the left-hand side, you can see that most of them are fine to review up to between 5, maybe 10 patches. And on the right-hand side, you can see that most of them are fine to wait up to 1 hour at most to wait for APR to generate patches. So the main takeaway would be the 1 hour timeout and the top 10 patches. Now, we also saw that developers seek low interaction with these APR tools, but they can provide additional artifacts like test cases, program assertions, and logical constraints. Also, we investigated the impact, like if the APR technique is using these artifacts, would be the impact on the trust on the auto-generated patches. And we saw that especially test cases would have a positive impact if they are used in the APR. Okay, so after the survey, we started with an experimental evaluation of existing and state-of-the-art APR techniques. We had two goals in mind. First of all, the collected constraints by the developers, and secondly, the impact of additional input like fixed locations and parsing test cases. We looked at a wide spectrum of APR techniques, search-based techniques, semantic-based techniques, machine learning-based techniques, and we looked at the many-box benchmark. And just to mention, our goal was not to show that any tool performs good or bad, but to actually investigate specific aspects concerning the adoption of program repair in practice. We have used the default parameter settings instead of fine-tuning or extending the tools. Of course, if you would do that, you could and you should get better results. All right. So the main takeaway from the evaluation was that it was very hard for the tools to actually generate the correct patches with these very tight developer constraints. This is different to a prior experiments in the original papers because they had the intention and they wanted to evaluate the capability to generate a patch. They did not look into this very tight timeout and also the top 10 ranks. Well, this is not too worrying that we got this result because APR tools are only at the beginning of to gain adoption and are still an emerging technology. So we wanted to understand, okay, what does it take so that APR tools can get to this standards of the developer constraints which we collected. So we made a couple of observations. First of all, of course, we want to have a rich search space because we want to increase the likelihood that the correct patch is in our search space. This can be supported by user inputs like fixed locations or user-specified constraints. Then if you have a rich search space, you also want to be fast in exploring it. So you need an efficient search space exploration. And such a construction of this traversing can be supported by patch-based abstractions like stun and fix-it and CPR. Then if you have a lot of test cases you want to incorporate, thank you, then it becomes necessary that you have an intelligent test selection. And also at the end, it will become necessary to have a good patch ranking mechanism, which also was a very important result from our developer survey. So how do we get closer to trust? Well, developers want to have the last saying. They want to review the patches which were auto-generated. So we had three basic insights on how to do that. So first of all, the developers want to see insights why the patch is targeting the right issue. Secondly, they want to see the evidence on the correctness of the patch. And first and finally, they want to have easy accessibility of the patches. Many of these aspects can be already supported by API side products like the identified fault locations and inferred repair constraints, but we definitely also see the need for more research in patch explanations, patch rankings, and the efficient traversal of the abstract patch space. Our material is evaluated and available. Thank you very much for your attention, and I'm looking forward to discussions.
Amazing talk. Now we'll have the last presentation of the session, which is causality-based neural network repair. This work is also done by researchers from management. So let's hear it from them. So can we have the presentation, please? Yes, you can please start the presentation. Your screen is visible.
Okay. Can you hear me right? Oh, okay. Hello, everyone. My name is Sunbin. Yeah, today I'm going to share our recent work, causality-based neural network repair. So here, I'm not going to repair a software, but I'm going to repair a neural network. Yeah. In recent years, neural networks are widely adopted in different areas. Hence, its dependability and reliability is very crucial to us. However, similar to traditional softwares, neural networks can be wrong and it can also be misbehave in different ways. And here I show two examples. One is that the neural networks may raise fairness concern, or it may have backdoor embedded. Hence, there are needs to modify a neural network to fix certain defects. One major solution here is to retrain the neural network with additional data. However, this can be very difficult and expensive in real applications. Hence, in this work, we introduce CAD, causality-based neural network repair, as illustrated in this slide. It will take a neural network and the property as the input. It will first verify the property against the neural network. Then it will conduct causality-based fault localization to find the guilty neurons to the unwanted behavior of the model. And lastly, it will repair the neural network for better performance. So here in the first step is the property verification. And in recent years, there are plenty of existing works. Hence, in this step, we just adopt the existing approaches as listed down here. Then in the second step is doing the fault localization. When we debug a traditional software, it's all about reasoning over causality. But when it comes to neural network, it will be quite different because the unwanted behavior can be a collective result of all neurons in the neural network. But it is also true that not every neuron contributes the same to the unwanted behavior. So here comes our question, how do we quantify the responsibility of each neuron? So in this work, we rely on this thing, average causal effect, where we want to measure the causal effect of a variable X on the outcome by performing intervention on the variable. And one simple example is that the ACE of taking a drug is the difference between the average effect of a population taking the drug and the average effect of the population not taking the drug. And in this step, we measure the ACE of all neurons in the neural network, and we find the most outstanding neurons are the guilty neurons. And in the last step, we apply particle swarm optimization to optimize the weight parameters of those guilty neurons and construct the repaired network. Our approach is evaluated over 3 different tasks: fairness repair, backdoor repair, and safety repair over multiple models trained on benchmark datasets here. And this slide shows the overall performance or the average performance of our approach. The first row here highlighted is the average performance of CARE on 3 different tasks. As you can see, we can improve fairness by over 60%. We can remove about 99.9% backdoor, and also we can improve the safety performance by 99.7%. And the cost in model accuracy is below 2%. We also compare with the sole tasks like DTMC and then repair and pardon, and we can see the results actually on average, CARE has better performance. Yeah, in conclusion, in this work, we propose and implement CARE as an automatic neural network repair tool, and we demonstrate the effectiveness of CARE on the context of 3 different tasks. And we also empirically evaluated CARE on multiple neural networks on benchmark datasets. And the results suggest that CARE improves the performance at very low cost, and also it outperforms existing SOTAs. Yeah, this is the end of my presentation. Thank you.
So thank you for the presentation. We can now take up the questions starting from the first paper. So the first paper was on evaluating automatic program repair capabilities to repair API misuses. So do we have any questions for this paper?
Okay, can I ask the question about the API misusage? I mean, you have the benchmark around 108 API misuse APIs. And then what's the characteristic for that benchmark? Is it coming from the standard like Java API or from the very project-specific invocation API?
Okay, thank you for the question. So we investigate Java APIs. So we are interested not in simple bugs, let's say, like missing null checks, like if conditions and things like that, that maybe existing repair tools can repair so far. We want to see whether the tools can repair, for instance, missing calls from APIs. So you haven't called an API, let's say, or missing exception handling, for instance. So you don't use correctly the specification from the API. We can consider different APIs like the Java API, the JDK, or APIs from Apache libraries, for instance, third-party libraries and things like that, but all from Java. Yeah, I don't know if I have answered the question, but yeah, we consider Java APIs.
So any other question from anyone? Yeah. So tool or the research that you have done, does it also detect the APIs which might be, imported, which might be used priorly at a point in the software, and over the time as they progress through various releases, let's say the usage is now changed, API is not being used now. So what I mean to say is that the API software is not being used. So does it also detect those conditions or those scenarios?
Okay, thank you very much for the question. So I guess that, Ritu, you mean about deprecation of APIs. So we haven't considered these cases yet. I mean, we don't check whether, we consider that the API, it is used. So we don't check deprecation at this stage. So we don't check whether the API is updated. We just check the use. Yeah, so we don't consider deprecation so far, but this is something that we can do in the future, of course.
So let's move to the next paper. Thank you, Maria, for answering the questions.
Thank you.
To the next paper, do we have any for the second paper of the fault localization and program repair with deep semantic features and transport knowledge? Do we have some questions for this paper?
Hi, Ritu. I see a question from the chat list. Maybe I should ask her. Are you offline? Hello? Is she offline? So I will give an answer to Shangwen. Are you there? The question is, if the transfer PR is to prioritize the repair pattern, why it can fix more bugs than T-bar? Okay, this is a good question. And well, in a common repair setup, if a generated patch passes all the test cases, the fixed process stops at once. But in fact, this patch may not semantic correct after human verification. So if the order of templates is not considered, the repair templates defined in T-bar can fix 71 bugs. However, due to the order in which templates are tried, some repair templates that will generate plausible but not correct patches will be selected earlier, resulting in repair failure. So T-bar finally can fix 62 bugs in perfect localization setup, and our method can optimize this problem, can fix 5 more bugs. So I don't know if I explained it clearly. Hello, Shangwen. Okay, thank you.
Can I also ask a question about the fault localization? So I mean, it's very nice to see that you do the fault localization and the repair, like the joint work. And I mean, for some bugs, repair is very easy by only deleting the code. But that's actually have a very hard work for the fault localization, because you don't know which part of statement you want to delete, or the block you want to delete, or even like you want to unwrap the condition. So it means that you need to have a very precise fault localization even for the delete bug. So I'm wondering what kind of the granularity in your fault localization is considering.
Okay, thank you. That's a good question. And I mean, you want to ask my standard of statement level fault localization?
Yes, because
such as delete some statements. Yes. Okay. For Defense4J dataset, I used the annotation from the Defense4J's order. So his paper from his paper in HC 2017. Yeah, the statement level annotation. Yeah. About how to construct my statement level dataset, I gave a list of standards which is defined in my syntax tracker, and I will open source it as soon as possible. If you're interested, you can refer to my GitHub repository. Thank you. So is our chair offline? Maybe next. Okay.
Thank you for that question. I'm sorry, I faced some network issues at my end. So let's move to the next paper. The next paper, which is neural program repair using execution-based propagation. So can we have some questions for this paper?
I have a question.
Do we have the authors? Yes. Let me just check with the authors first.
I would like to know, after adding program compilation and test case running, during the training phase, will the training time become too long? Thank you.
Yeah, it's very long, and sometimes it can't have the time out, but it's just actually the normal time when you execute possible
Can
patches.
I
And
can you please type in your question in the chat box as well?
yeah, I heard his question. It's okay. So and he is just asking the how much time do you take during the training? So because in our training it does not take a lot of the semantic training samples, because our interpretation is that one semantic bug sample actually is provided environment and with the context. And in this environment, the neural network can actually give a lot of generate a lot of the predict samples in there. And then in this specification, you can note if your code is compilable or is not, and then it gives you a feedback.
Okay, thank you.
So let's have questions next paper, which is trust enhancement issues in program repair. Do we have any questions for this paper? Trust enhancement program repair.
Yeah, I also have questions. Sorry, I have a lot of questions. And so in the trust issued paper, so it's done in the
I have a
Bugs
question.
benchmark.
Do you have actually tested live scenario as well, your research?
Okay, I think we now have two questions. Maybe yeah, okay. First, I answered for Ritu. So the listener, we did the survey. I mean, we asked real developers, but we did not do, like, we did not have a study, if you mean, like, we did not deploy API techniques with developers and observe them. This is not what we have done. So we just issued the survey and got the responses. Yeah, but it would indeed in an interesting future work. Yeah.
Okay, thank you.
Yeah. I think there was another question which was interrupted.
Yeah. My question is that because I saw the experiments from your replications, like the in the many bugs benchmark, there's not as many as the possible and the correct patches generated in diffs4j. So I was wondering, what's the different characteristics between the many bugs and the diffs4j benchmarks? Because in the diffs4j benchmark, we normally like have around 50 correct patches generated. So this is something I probably will need your knowledge to share about.
Yeah, that's a good question. To be honest, I'm not too familiar with the defects4j benchmark, because we are more doing the current out tool for C and C++. Yeah, I think I'm lacking here a good answer.
It's okay, we can figure out together.
I don't know, maybe one of my co-authors knows more about that, but yeah.
What's the question? Sorry.
I think Abik has something to say.
What's the question? Sorry, can I get the question?
The question was, what's the difference between the many bugs benchmark and the defects4j benchmark, besides the language?
Oh, okay. I think, yeah, so Ridwan probably can answer as well, but the defects4j, I think primarily more shallow bugs, right, as I understand, and also lot of issues with libraries, etc., as compared to many bugs where some of the patches are rather complex. Yeah, the patches are rather complex, because that's not very surprising also, given the difference in the programming languages, because C is a rather low level programming language. So it's sorry, my video. rather low-level programming language, so it's possible to make kind of many kinds of errors, and the fixed space also very easily blows up, and it's possible to, as soon as it's possible to make many kinds of errors, then you can sort of fix the error in different locations, and in each location you can fix in different ways. So effectively, even for a relatively decent sized program, the fixed space, the search space very easily blows up, even though the program size. So as we know, the difficulty in program repair doesn't come from the scalability of the program size, which often people mention, but rather scalability in terms of the search space. So I would say the search space, this may not be exactly the answer you are looking for. Hey, but this is probably the answer you are not looking for. But the search space in many bugs is probably much bigger than the search space of the defects of a defects4j program of the same size, just because of the way but exactly like what kind of bug you were probably looking for, a more directed answer, like exactly these bugs are more prevalent in defects4j versus these bugs. That one of course requires a little bit more. I would need to go back and refer to the both and give a more detailed answer, but it would be fairly safe to say that effectively the search space is much bigger. As a result, repairing is quote unquote harder. At least the search space is bigger. Yeah. Very good to see you. I hope you are finishing your PhD soon. Yeah.
Yeah, very nice to see you, Arvik, and I really like your work. So because I added the ranking information in our RQ3 after I read your paper, because I think the ranking information is very important. And you state like a developer favors the top 10 within the 1 hour. And then in this 1 hour, it includes the both like the patch generation time and the patch verification time, right? Like
Yes.
so in the tools you have experiment like so what's the propagation for the generation time and verification time, so how much time it take for generated?
Yeah. So Yannick, you have the breakup, the exactly how much of it was generation, how much was validation.
Yeah, I think.
Go ahead.
Yeah. So we have 1 hour in total. I think we made 50-50.
Yeah. So this is one thing. Also, this 1 hour actually is very tight limit. So you will see the results that were reported, they appear to be significantly less favorable than the results that have been reported in the research papers. And that's simply because we are imposing a very strict timeout. It's as you pointed out, both the generation and the validation, everything in 1 hour, and that also using the default parameters. If you have a slight heuristic that, okay, for these kind of programs, these parameters should be changed little bit. So it's possible to customize a little bit, and even little bit of these kind of changes can improve the results. But this is sort of the baseline. That means this is what can definitely be achieved out of the box, but presumably better. But this is what probably, let me put it this way, a naive user of the program repair tools with a very little tolerance for time, this is what they would produce basically.
Yeah, yeah, definitely. Particular when we need to enumerate all the suspicious lines from fault localization.
Right. Yeah. Thanks. Hi. Yeah.
Thank you.
Okay, thank you for the discussion. And now let's move to the questions for our last paper, which is causality-based neural network repair. Do we have any questions for this paper? So, if we don't have any questions, can I ask the authors to discuss any challenges that they faced while conducting this research?
The challenge in the research actually is the main problem we need to solve when we work on this approach is how can we identify the contribution of each hidden neuron in the neural network. So when we first look at this issue, we try different methods. We try the sensitivity analysis or gradient-based method, or we just pick some most active neurons in a network and do the optimization, but the outcome is not so good. And finally, we come across with causality-based analysis, and the result is very good. And also, we have shared this comparison result for different fault localization techniques in our full paper. Yeah.
So I would like to thank all for conducting the different presentations in this research, in this session. And then let's see you around NXC. Please enjoy the other sessions. Let's go. Yeah, thank you.
Thank you.
Thank you. Bye-bye.
Thank you.
Yeah, bye-bye.